Okay, well, first, thanks a lot for organizing and for the invitation. It's the first time I have a chance to visit, so it's really nice to be here. For those of you who don't know, I actually also forgot to put it on the slides, but I just recently moved to UC San Diego, so it's much closer and easier to visit now. And so I'll talk about primordial black hole dark matter, as the title says. I think for this audience, I could probably start with the main discussion right away, but I have one or two introductory slides. I wanted to make sure everyone is following along. The first one certainly is too basic, but just given that we're here, I thought I would include one slide that has Fritz Zwicky on it and the coma cluster, and then Vera Rubin and the measurement of light curves, just to illustrate that we have good evidence that there is dark matter. And I also included a plot of the angular power spectrum from Planck. Obviously, we also have polarization measurements, but this is just a reminder that the CMB, depending on exactly on which data sets or which parts of the data you're looking at, tells you at 80 to 100 sigma that dark matter is non-baryonic. So we know that with high confidence. There's not really any wiggle room. So we know something about it, but we don't really know whether the dark matter consists of WIMPs, which is kind of everyone's favorite, or was everyone's favorite idea for dark matter, or it consists of axions, which I think are equally well motivated. For example, if you think about the strong CP problem, there's good reasons to think that there should be an axion to detect. It's not clear it has to be the dark matter, but it's certainly a natural candidate. We also already heard about self-interacting dark matter. We'll hear about neutrinos. There's many ideas what it could be. We have no idea what it is. I'll just talk about one of these ideas, which are primordial black holes, which have recently become popular again. So this obviously goes back maybe 50 years or so. There's papers by Zeldovich and Novikov, so this really, the idea goes back 50 years. And it's become popular recently because LIGO has detected gravitational waves from binary black hole mergers. Now, at first sight, you might say, well, why is that related in any way? And I think it probably really isn't, but let's at least follow the logic. So the logic is what you're looking at here are binary black hole mergers, and it turns out if you make a plot of the various events or binaries observed in X-ray studies, binaries seen in LIGO, then you see that they're typically heavier. I'm not even sure that you would right away draw that conclusion if they were ordered in a different way, but I mean, there are certainly candidates that are significantly heavier. Some of them are not necessarily significantly heavier. So the idea is that they're more massive than you might have expected, and the question is, how did they form? There's, in astrophysical, black holes seem at least challenging to form in this mass range. The question is, how do you bring them close enough together for them to merge within a Hubble time? How do you make sure they don't lose most of their mass beforehand? So there's at least some work ongoing trying to understand what LIGO is actually telling us about astrophysics. Another path forward is to say, well, this might be a primordial black hole. So this is the idea that was put forward by the people I have on the next slide here. So this is the group at Johns Hopkins: Simeon Bird, Colis Munoz, Yassin Ali Hamed, Mark Kamiankowski, Eli Kovets, Racanelli, and Rees. And so the question they were asking is, could LIGO really be seeing mergers of primordial black holes that make up all the dark matter? And naively you might say, well, this must be ruled out by something else, and that's what we'll discuss. The other obvious question is, well, do the rates at least agree with what's estimated by LIGO? And that's what I'll start with. I won't go into the detailed derivations that people gave, but the basic idea is that you have this population of primordial black holes of about 30 solar masses, or of some mass in your head. You should keep the 30 solar masses. And then they scatter off each other, and as they scatter, they will emit gravitational waves. And once in a while, they emit enough gravitational waves that they become bound and form binaries. You can compute a cross-section for this process, for this formation of binaries. And that's what's written here, so it scales. The one thing to remember is that the Schwarzschild radius goes like the mass, so this scale goes like the mass squared. And then you can just compute the rate per volume in the usual way as the number density squared times the cross-section times the velocity of these objects. And you can slightly rewrite it in terms of quantities that you might be interested in. So this is the dark matter density in this case, which we know. And it goes like 1 over the mass of the black hole squared, which cancels the mass dependence here. So the rate that you expect is independent of the mass. And you can estimate it from Milky Way-like halo, and you find that the rate that you expect there is very slow, much lower than the rate that was inferred by LIGO. On the other hand, you see that there's a pretty steep dependence on the velocity, so you can ask, well, what if these black holes are in substructure? And it turns out that then you can get rates up to 700 per year per cubic gigaparsec. And in the paper, they're not just doing these back-of-the-envelope estimates, but there's also more refined estimates based on in-body simulations. And it turns out that the rates roughly agree with what you would expect if you wanted to explain LIGO. That doesn't mean that this is what LIGO is seeing, but at least the rates work out. And then the second question is it already constrained by other data? And so here I'm showing you a plot that's adapted from this paper, adapted in the sense that I took out constraints that weren't available at the time when the previous paper was written. So this paper came after the paper by Mark Kamienkowski and company. So I've taken out one of the constraints. I'll put them back in later. But this is what the landscape looked like when the paper was written. And I don't know if I should go through all the constraints, but certainly on the left, so black holes, Hawking evaporate if they're too light, so the lifetime goes like the mass cubed, so heavier black holes live longer. If they're too short-lived, obviously they're not the dark matter. So at the left, you can eventually cut off the plot. And then there's some regime where they live long enough, but they emit gamma rays that you can look for. So these are these extragalactic gamma rays that place bounds. So anything to the left here is just excluded. Then this is femto lensing. This is from Fermi data of gamma ray bursts. So here you're probing black holes that have comparable sizes to the wavelength, and so you get interference in the energy spectrum, which gives you constraints from the Fermi data. That's what's shown here. Then this little wedge here is from white dwarf explosions. So the idea is that you have these primordial black holes that travel through a white dwarf, heat it, and eventually it explodes. Here this constraint is... Sorry?
What is F?
F is the femto...
No, the F on the y-axis.
Oh, sorry, this is the fraction of the dark matter. So 1 means it's making up all the dark matter, and then here it means it's 10 to the minus 3 of the dark matter is in these black holes. Yeah, sorry, I should have said. But here's the mass, and maybe this axis for later will be more helpful to look at. So this is the mass in solar masses. Eventually, we were talking about 30 solar masses, which are somewhere out here. And yeah, so here, this is one of the, yeah, so, okay, I hope that helps. So this is the mass in grams, the mass in solar masses, and this is the fraction of the dark matter made up by these black holes. So this is the neutron stars. Is the idea that the neutron stars capture these black holes and they gobble up the neutron stars. So just the fact that we're observing neutron stars excludes black holes or primordial black holes in a certain mass range. And then here are the microlensing constraints using Kepler data. This is the Macho, Eros, Ogle surveys. And then here are the CMB constraints that I'll say more about. But this is, in any case, what the landscape of constraints looked like. And the statement then in the paper was that, well, the phi-RAS and WMAP constraints are model dependent, and we'll ignore them. So this is the kind of plot that was used to argue that there is a window around 30 solar masses. And I'll get back to the CMB constraints. So this is something we were looking at. Yeah? There, in a second it will be gone because there's now new data from Subaru, but there's additional data, but it's okay, yeah.
There's also extragalactic microlensing data that rule out that interesting range there. Like, not much, but like the opposite big extragalactic microlensing.
Here you mean?
No, so around 30 solar masses.
From 10 to 30?
Yeah, it's the range there. Maybe it's not plotted there, but there
Yeah.
is some data around as much.
So this is what I was saying. So there is a separate constraint, fairly recent. It's from January 2017. This is relevant for the discussion of the neutron star range that is coming from pixel lensing with the Subaru telescope, which is ruling out a fair amount of range. So this is just staring at the Andromeda, or M31, and this rules out a fair amount of this range. And then these constraints are by Tim Brunt from 2016, where he pointed out that the existence of a globular cluster inside the Eridanus II dwarf galaxy that was observed with DES actually rules out this mass range. And then there's additional constraints in his paper that are not really plotted here from ultra-faint dwarfs that rule out a similar mass range. So there's a fair number of data that's ruling this out. And there's also, if you wish, loopholes that people are trying to exploit. So for example, you could imagine that at the center of this, so the idea of the globular cluster is just that if you have these black holes moving through the globular cluster, it will heat them, it will get puffier, it wouldn't really look the way it does. So you can try to cancel that in some way, and it turns out if you imagine having a 10 to the 4 solar mass black hole at the center of that cluster, you can maybe avoid the constraints. I'm not sure how natural that is, but there are some ways that people are trying to wiggle out of these constraints. So the ones I wanted to talk about, because that's the ones we were looking at, are the constraints from the cosmic microwave background that were taken out because people said they were not correct. And certainly the Phi-RAS constraint, well, let me do it in order. But so there's two ways that these primordial black holes affect the cosmic microwave background. Well, in both cases, it's the fact that these primordial black holes accrete matter, and you get some effect on the baryon photon plasma. So if you think about the plasma at a temperature, let's say below 10 to the 9 Kelvin or so, after the electrons and positrons have annihilated, the contribution here is dominated by the time around recombination, so it's fair enough to think about it at those later, relatively late times. So you start at 10 to the 9 Kelvin, so you have a plasma that's made up of electrons, protons, helium, and some other trace elements, photons, neutrinos, and dark matter, in this case the primordial black holes. And then you have Coulomb interactions between the charged particles, between the electrons and the ions, the nuclei. You have Compton scattering between the photons and the electrons, double Compton scattering, Bremsstrahlung. So you have effects that exchange energy and momentum efficiently, and that change the photon number. So you generate a black body spectrum at these at 10 to the 9 Kelvin or so. As you run the movie forward, eventually some of these processes freeze out. The photon number changing processes freeze out at a redshift of about 10 to the 6 or so. It's relatively easy to estimate these things with some back-of-the-envelope estimates, and if anyone is interested. And so if you inject energy or photons at a time later than this, you generate mu distortions. If you go to even later times, eventually energy is no longer efficiently exchanged, just because the typical energy in a photon is of order the temperature. If you scatter, the momentum in the electron, the change in the momentum of the electron is also of the same order of magnitude as of order the temperature, but the kinetic energy, the change in the kinetic energy, is of order p squared over 2m, so it's kT over m times t. So if the temperature is much below the mass, then eventually you're no longer exchanging energy efficiently. This happens at around 10 to the 5 if you plug in the numbers. And so at that point, you're also no longer generating a Bose-Einstein distribution. You just end up with with intermediate and Y distortions, also recombination lines, etc. Here's the Y distortions that are generated by these black holes. And this is also not something we pointed out. This was pointed out a long time ago in a paper by Ricotti, Ostreicher, and Mack. And the one thing, that was done in that paper is there's powers of the scale factor wrong in one of the equations. So the only thing we did is fix that equation, compute the spectral distortions, and you see that the spectral distortions that are generated by these primordial black holes are actually quite small. So they're at the level of 10 to the minus 8, which you should compare to the phi RAS bound, which is at the level of 1.5 times 10 to the minus 5 at 95% confidence level. So there's really no significant constraints on these black holes from spectral distortions, not with phi RAS, but also not with proposed CMB missions. I mean, as people probably know, Pixie wasn't selected, but also other ideas would have a hard time testing these kind of signals from the primordial black holes. So spectral distortions is just not really the way to test for these primordial black holes. But this is also not the only effect the primordial black holes have on the cosmic microwave background. So the accretion onto these primordial black holes, it also heats the plasma, ionizes hydrogen. It really changes the ionization history of the universe. So you have a much larger floor of free electrons around if you have these primordial black holes. So here it's shown, the plot is showing the free electron fraction as a function of redshift for different models. So this is the standard scenario where you have no primordial black holes, is shown in blue. And then I'm showing where all the dark matter is made of these primordial black holes with a mass of 1 solar mass, 10 solar masses, and 100 solar masses. And if you've seen these plots before, then you notice that I'm ignoring something here at low redshift, which is reionization. This is just to, I mean, in the computations, it's obviously included. This is just to illustrate the effect of the primordial black holes. But there is, at redshift, let's say less than 8 or 9, you get free electrons again from reionization. So there's a modification to the ionization history of the universe, which clearly affects the cosmic microwave background. And
so that's a Bondi accretion kind of assumption?
Yeah. So in what we're doing, we're really assuming the same accretion model as the paper that I was showing, the Ricotti, Ostreicher, and Mack paper, which is Bondi. It's not just spherical accretion, so you include the fact that they're moving through the plasma with some velocity, and you take a thermal average. So there's for Bondi accretion, I guess it's the pressure that eventually limits the amount of material that's accreted. If you move, there's also a contribution from the velocity, and the formula that is average is a thermal average of 1 over the speed of sound squared plus the relative velocity squared, which is very well known because it's just the relative velocity between the dark matter and the baryons squared cubed. So it's something like 1 over v to the 6th thermal average, and that's what's assumed here for these models. There's a question of whether, I mean, certainly it's a good question to ask about the accretion models because it's, I think, the largest uncertainty. It's a pretty well-defined problem because we understand the plasma extremely well, and in principle something that can be worked out, but I think it's not been completely worked out. So there's certainly uncertainty in how this is modeled. Okay, so here's the plot. It just shows you what the effect is on the anisotropies. And blue, again, is what the spectra look like without any primordial black holes, just standard CDM. And then orange and red shows you what happens if you have 10 or 100 solar mass black holes making up all the dark matter. And you get a pretty clear idea that 100 solar mass black holes are probably not allowed by the CMB. Obviously, if there's degeneracies, and one has to be a little bit more careful, but the CMB really strongly rules out above a certain scale. Exactly what that scale is still a little bit up for debate. So if you run the analysis and look at what the contours look like, here I'm just showing you one that has a little bit of a degeneracy as you go to higher masses. But the main point here is really this exclusion plot. So everything to the left here is allowed, everything to the right in terms of masses. So this is the log with a base 10. So this is something like everything larger than 5 solar masses is disfavored by the Planck 2015 data, assuming the accretion model that I just said. So that's the largest uncertainty, I think. But in principle, there are these constraints. So there's no constraints from spectral distortions, but there are fairly tight constraints from the anisotropies of the cosmic microwave background. Maybe we haven't worked them out at a level that's required to really conclude whether the 30 solar mass black holes are allowed or not, but certainly there are these constraints. Yasin spent some time modeling the accretion, found that it accretes much less efficiently than the simple model I just said, and concludes that it's really black holes of larger than 100 solar masses that are ruled out, but the 30 solar mass black holes are not ruled out. There's another paper that modeled the accretion using accretion disks, claiming that accretion disks form at a redshift after recombination, and this gives them a bound suggesting that masses with larger than 2 solar masses are ruled out. Now, one thing I also wanted to discuss is just how one imagines these primordial black holes form. And one way is easy to see that they can form from the primordial power spectrum generated by inflation. So this is just the usual slow roll formula. You see that there's a 1 over epsilon in this. So if you have a period where epsilon goes to 0 or becomes very small for a while, then you really enhance the amount of power. This is not something that's particularly natural. It gives you a model that looks like this, but this is one of the proposals for how you might form these black holes. Then the question is why you put the dimple here, why you didn't put it somewhere else along the way. You can put it anywhere, really. There's not a clear rule why it should be here, but if you want to produce 30 solar mass black holes, it would have to be here. To me, it's not totally natural, these kind of things. But so there's also ways to produce them during reheating or during a phase transition, except for reheating, which really gives you some physical scale. It's just the horizon scale around that time. The ways to generate them during inflation or during a phase transition, they really don't naturally predict 30 solar mass black holes in any way. You can arrange it, but it's not really a natural prediction. And the reheating is very small black holes, so it's not really related to the black holes for LIGO. So this is basically what I wanted to say. It's just an update on what the various constraints are on primordial black holes. Just the basic idea, I think, is quite intriguing that LIGO might have seen gravitational waves from black holes that make up all the dark matter. To me, it seems disfavored by data, but this is always a matter of opinion of who looks at the data. And I think to have draw a firm conclusion, we need to really model the accretion onto these black holes better if we want to use constraints from the cosmic microwave background. There's also often a monochromatic initial mass function assumed rather than really a distribution, so there's ways you can still squeeze it in. What is nice, I think, about the idea is that it's really testable because it predicts a number of things that you can look for, like high eccentricities. You wouldn't expect any electromagnetic counterparts. You don't really expect them to be spun up like you might for astrophysical black holes. You would expect the signal to come from low mass halos, although there was a paper just 2 days ago by Mark where he's claiming that there could also be a signal from the near the center of the galaxy. Also predicts a stochastic gravitational gravitational wave background. And so I think this part is interesting. To me, it looks close to ruled out, but I think it's still interesting to explore and understand whether it is or isn't ruled out. So I'll just leave it at that, maybe.